This conference will now be recorded.
Good evening, students. Today we are back with the solutions of NEET UG 2023 physics paper. So we have few questions today for discussion. Let us try to solve those. So the first question says, in a plane electromagnetic wave traveling in free space, the electric field component oscillates sinusoidally at frequency of 2 into 10 to the power 10 hertz, amplitude 48 volt per meter. Then the magnitude of the oscillating magnetic field is 1.6 into 10 to the power minus 8 Tesla, or 1.6 into 10 to the power minus 7 Tesla, or 10 to the power minus 6 Tesla, or 10 to the power minus 9 Tesla. So you have to answer this question where the speed of the light is given. So this is very simple question. Here the magnitude of the amplitude of the electric field is given. Amplitude of the electric field is given. That means this is given as 48 volt per meter. Okay, and as you know, electromagnetic wave, both E and B, actually these are amplitudes, both E and B will oscillate with the same frequency, oscillates with the same frequency, with same frequency, but in the perpendicular direction. Okay, but in the perpendicular direction. So here what you need to remember is that E0 by C is equal to B, where this is B0 amplitude. So C is the speed of light, which is given here, speed of light in vacuum. So we can now see this is given, E0 is given, so B0 will be 48 volt per meter divided by 3 into 10 to the power 8 meter. So this will be in Tesla, since it is in SI unit. So you look here, it will be 16 into 10 to the power minus 8 Tesla. If you make it see 1.6, then it will be 10 to the power minus 7. Okay, this is 10 to the power minus 8. So this is the answer. Okay, so this was very simple question. Now we'll move on to the another question. If the galvanometer G does not show any deflection in the circuit shown, the resistance R is given by 50 ohm, 100 ohm, 400 ohm, 200 ohm. So you have to answer the question. Look here, if there is no current, okay, in this particular branch, if there is no current, then it means that the potential difference across it is 0. So look, if I write the potential at its junctions, you can see at this particular position it will be plus 10 volt. This is anywhere 0, this is also 0, this is 0. And at this position, see, it is actually plus 2 volt, then obviously we can say this also will be plus 2 volt, so that there is no potential difference across this galvanometer. So that's why there is no current flowing. Okay, the current flowing through this is 0. So this is the thing. Now we have to find out the resistance, value of the resistance. So since there is no current flowing in this way, so the current will be flowing through this way. Okay, so that's what we can see now. Look here, resistance is this resistance, this is another resistance. Okay, so current through this will be, the current through this will be 400 ohm, will be 10 minus 2 divided by 400. So this will be the current through it. Okay, now see, this will be equal to 8 by 400, which is in ampere, 1 over 50. Right, now see, the potential across this R is 2. Then see, I can write I through R will be 2 volt by R, and this is exactly equal to the current through this. Right, so then I can write this. So this implies that 2 by R is equal to 1 over 50 ampere. Okay, so both side ampere will be cancelled. So I can write R is equal to 100 ohm. So this is the answer. Okay, so 100 ohm is the answer. We move on to the next problem. Okay, so this is reasoning based question. Given below are two statements. Photovoltaic devices can convert optical radiation into electricity. This is correct. We know optical devices, actually, if you just think of solar cell, there's a photovoltaic cell. Okay, that consists of photovoltaic cell. What is the purpose of photovoltaic cell? Is that when photons are coming, okay, photons are coming, they are absorbed, and that photon or light energy will be converted to electricity. Okay, so electricity will be generated. So this is, see, one example is solar. So where solar energy is converted to electricity, that is true. Zener diode is designed to operate under the reverse bias in breakdown region. This is also true. This is also true. So both statements 1 and statement 2 are incorrect. Both the statement 1 is correct. Oh, sorry, the statement 1 is correct, and but statement 2 is incorrect. Statement 1 is incorrect, but statement 2 is correct. Here the last option says both statement 1 and statement 2 are correct. So D will be correct option here. Okay, so Zener diode is actually specially designed to operate under the reverse bias condition at the breakdown voltage or breakdown region. Now let us go to the next problem. The errors in the measurement which arise due to unpredictable fluctuations in temperature and voltage supply are called random errors. So this is random error. Okay, so personal error is different, that does not depend on fluctuations, etc., that is inherent with any person. Least count error, that depends on the instruments. Okay, that does not depend on the temperature and voltage fluctuation. Instrumental error, anyway, it is depending on instrument. Random error is the one which comes randomly due to change in the fluctuation of the temperature and voltage supply, which we cannot actually estimate. Okay, we'll go to the next problem. If this closed path integral of E dot ds is equal to 0, what does this mean? This means flux is 0, total flux or net flux is 0. Net flux coming out through the closed surface is 0. From a surface coming out of a surface is 0. Closed surface is 0. Coming out of a closed surface is 0. So total flux coming out or net flux coming out of a closed surface is 0. Then which among these options are correct? You have to is correct. You have to find out. The magnitude of the electric field on the surface is constant. Actually, that doesn't matter. If electric field is constant, in fact, electric field has to be constant in any case. Okay, but for that, net flux will not be 0. All the charges must necessarily be inside the surface. Okay, if all the charges inside the surface, then net flux should not be 0. That is not the actual reason for getting net flux 0. The electric field inside the surface necessarily uniform. This is also not the reason for net flux to be 0. The number of flux lines entering the surface must be the number of flux lines leaving it. This is correct. Okay, it is. See, if if there is a surface like this and the number of flux entering, they are just coming out, so what will be net flux inside? There will be nothing. So that is the reason. The number of flux coming in and going out or leaving the surface are the same. That's the reason the net flux is 0. Let us go to the next problem. An AC source is connected to a capacitor C due to decrease in its operating frequency. Displacement current increases, displacement current decreases, capacitive reactance remain constant. Okay, and capacitive reactance decreases. Okay, look here. First of all, let us find out. See here, frequency of operating frequency increases. See, if I just take parallel plate capacitor and let us connect this plate with alternating battery, since the frequency is changing. Okay, so the frequency can be changed. Frequency is there, means this is AC anyway. So what happens at particular, see, generally excuse me, generally AC signal Generally, AC signal we take as sine curve or cosine curve. This is sine curve, symmetric curve generally. So what happens? Capacitor during this cycle, okay, positive half cycle, it gets like a quarter of the cycle it gets charged, and another quarter it gets discharged. So in the opposite direction, quarter half cycle it gets it quarter cycle it gets charged, again discharged. Okay, this happens actually. But anyway, the thing is that the electric field in between will be uniform, and that electric field can be obtained as sigma by epsilon naught if this is air medium in between. Okay, and see from here, see I have to find out displacement current. I can actually do one thing. I can just multiply E into A, that means sigma into A divided by epsilon 0. See, this is nothing but Q. So Q by epsilon 0, that is equal to, see, this is E into A. I can write this as electric flux. So Q can be written as epsilon 0 into phi E. So what is the current? I can write displacement current ID is equal to dq by dt. See, crudely we can write this is epsilon naught into d phi e by dt. So what is the expression for the current? Displacement current is the expression for displacement current is excuse me, yes. So displacement current we get epsilon naught d phi e by dt, or in other words, or explicitly we can write, see, A will be anyway constant. So this is the expression for the displacement current. Okay, if I just remove all this, all right, so this will be displacement current. Okay, now look, if the electric field, frequency of the electric field changes, then what happens? This current also will be changing. Why? Because see, if the electric field changes, then this factor will change actually. So here, due to decrease in operating frequency, if the operating frequency changes, that means, see, operating frequency changes, see, that means, you know, the electric field changes its value. Electric field changes its value, as you see here. If the frequency is very less, then change in this quantity, this particular quantity will be actually less. If the frequency is more, then this change will be more. D by dt, this change will be more with respect to time. So that's how here, if due to if the frequency, operating frequency decreases, then obviously displacement current also will be decreasing. So that's why option B will be correct option here. Okay, we'll move on to another question. See, the minimum wavelength of X-rays produced by an electron accelerated by a potential difference of V volts is given by. So wavelength of minimum wavelength of X-rays produced. Okay, so it is actually very simple. If you have remembered this thing or memorized, that is very nice. This is 12.27 or 28, 12.28. This is in angstrom divided by volt. Okay, this is actually the formula, or we can say this is this. Okay, you have to just remember this formula, or else we can find it out. Okay, we know E is equal to h nu or hc by lambda, hc by lambda is equal to hc by lambda. Okay, so what is lambda then? Lambda is equal to hc by e. What is this e? What is this e? This e is actually, see here, e into v. Generally e into v, this is actually kinetic energy. So p square by 2m, generally kind of de Broglie wave if you do, p square by 2m. So all right, but okay, better to don't go in this detail, better to be with this thing, be satisfied with this, and remember this formula. Okay, so option B will be correct here. Now we'll move on to the next problem. This is the Venturi meter works on. So Venturi meter works on the principle of Bernoulli's principle actually. Okay, this is from fluid mechanics or mechanical properties of fluid. Venturi meter Venturi meter. So how does that look like? You know this. I'll just show you. See, generally there will be a tube, or see, it looks like this. It has wide area over here. Okay, wide area, and then there will be narrow tube here, and it connects another wide part here. So this both of these have same area. Okay, both of them have same area, and here generally a U-tube manometer will be connected. Okay, U-tube will be connected, kind of this. My drawing is not becoming so perfect, but this is okay. Just a minute, I'll try to draw it properly. So there will be U-tube here. Okay, So this is actually the Venturi meter, and the flow velocity will be calculated. The flow velocity is v1 through this and v2 through this. Okay, and see pressure will be different here, something like P1, and here something P2. Okay, P2. So due to this pressure difference, there will be flow of liquid. Okay, flow of liquid here through this, and it has flow velocity v1 is equal to square root of 2 p1 minus p2 divided by rho. If the density of the liquid is rho, then let us say this is A1 is a area and A2 is here. Area of this part is A2. So it will be A1 by A2 whole square minus 1. And this rho will be whole into this. And the whole part is inside the square root. Okay, so this is how this actually works on the principle of Bernoulli's effect or Bernoulli's principle. So I think this is not V, this is Bernoulli's B, Bernoulli's theorem, Bernoulli's principle. Okay, this works on Bernoulli's principle. All right, so we'll go to the next problem. A full wave rectifier consists of two p-n junction diodes. A full wave rectifier, it consists of, see, I'll tell you, full wave rectifier. How does this look like? Circuit diagram. How is the circuit diagram? Do you remember that? Circuit diagram is very simple. See, there are actually four diodes. I'm sorry, the full wave rectifier, there are actually two diodes. Okay, full wave rectifier consists of two diodes. Okay, so there are two diodes and there will be center tap. See, this is one transformer and it has center tap here, C. Okay, so this is A and this is B and this is C, center tap, and there will be two diodes connected. One is here and center, there will be load over here. Okay, so load over here, and through load both the diode will be connected. Okay, this is how, and here this is the secondary coil of the transformer, and here in this way there will be primary coil of the transformer. Okay, so primary coil, so there are two diodes, and the rectified output, full wave rectified output will be kind of this. So this is the rectified output. Okay, but see, even though this is DC, there is no negative value of the output, but still it is not a constant value, right? It is actually oscillatory in nature. This oscillatory nature is called ripple. So this ripple is actually rectified by or or remove this ripples are removed by a capacitor. Okay, so the question was here, a full wave rectifier circuit consists of two p-n junction diodes, a center tapped transformer, capacitor, load, resistance. Okay, so how do we which of these components removes the AC ripples from the rectified output? So rectified output is oscillatory or wavy in nature, which is called AC ripples. So this wavy nature will be rectified with the capacitor, okay, or remove. These ripples were removed by a capacitor. We'll go to the next problem. So this is a metal wire has mass 0.4 0.002 gram. This is gram, and it has radius. A metal wire has a radius. Radius small r is equal to 0.3 plus 0.001. This is millimeter in radius, and length is 5 plus 0.02 centimeter. So maximum possible percentage error in the measurement of density will be 1.3 percentage, 1.6 percentage, 1.4 percentage, 1.2 percentage. You have to find out which among these option is correct. See, first of all, let us write what is the expression for density. Mass density rho is m by v. Again, it is a cylindrical wire, so v is the volume. V can be written as pi r square L. Now look, to find out percentage error, maximum percentage error, we need to take logarithm, okay, and with for maximum possible error, we will write all of them with positive sign, okay, ln pi plus 2 ln r plus ln L. Okay, now you have to take derivative of each of them. See, I'll take derivative of rho with respect to rho itself. So del rho by rho. So this will be similarly del m by m. Okay, and see, pi is a constant. It has a constant value, so no change in that. So that's why that will be 0 plus 2 delta r by r. What are these delta r, delta m, and delta rho? These are the error in the measurement. So mass, in the measurement of mass, there will be some error, that is delta m. In the measurement of radius, there will be some error, that is delta r. And see, this will be delta L by L. Now look, these values are given here. Delta, this is actually m, this is delta m, this is r, this is delta r, and each of them I am writing here in terms of ratio. So that's why no need to change the units, because units will be anyway, these are ratios, so units will be taken care over there, they will cancel each other. So del m will be 0.002 divided by 0.4 plus 2 into delta r is 0.001 divided by, that is 3.3. Similarly, we'll write for L also, delta L is 0.02 and L is 5. Okay, if you do the calculation part properly, see, look here, 2 into 10 to the power minus 3 and 1 from here, it will go to there, so it is 10 to the power minus 2 divided by 4 plus, this is 2 into 10 to the power again minus 3, 1 will go there, so 10 to the power minus 2, here 2, sorry 3, and the third one 2 is 10, 2 into 10 to the power minus 2 divided by 5. Okay, so this will be half, this will be 2 by 3, and this will be again 0.4. Okay, this will be 0.4, so this will be 0.5, so 0.9 is fine. And see, there will be 10 to the power minus 2. This is absolute value. If we want to make it percentage, so we have to multiply with higher than 100, so this will go off. So 0.5 plus 0.4, and this value will be actually 0.6, something like 0.6, so it will be 0.67, you say. So you will get actually 1.6, so 1.57 kind of that, so that will be nearly 1.6. Okay, that will be nearly 1.6. Okay, so we get error, percentage error to be 1.6. Okay, all right, 1.6 percentage. So we'll go to the next problem. So this is a nice problem. You see, it is from wave optics. For Young's double slit experiment, two statements are given below. First statement, the first statement is saying that if the screen is moved away from the plane slits, if the screen is moved away from the plane sheets, angular separation of the fringes remains constant. And the second statement, okay, second statement is, so it is actually about angular separation of the fringes and how it depends on the distance d. See, generally slits will be like this. Okay, so slit 1, slit 2, double slit, and the screen will be there. So this distance is called capital D, and generally here will be central bright fringe, CB, central bright fringe, and then one by one bright and dark fringes will be appearing on the screen. And see, this angle is actually theta. This angle is theta, and this angle is actually same. This theta is same for all actually. This angle is same for all of them. That means fringes have actually same angular separation. Okay, same angular separation. So the question is, if the screen is moved away, that means d is increasing. Okay, if the d is increasing, what will be the angular separation, whether the angular separation of the fringes will be remaining constant or that will change, that we have to see. If the monochromatic source is replaced by another monochromatic source of larger wavelength of the angular separation, then the angular separation of the fringes decreases. Okay, so in one case it is said that it remains constant, and another case it said that if the wavelength is taken larger, then fringe separation will be, angular separation of the fringes will be decreasing. Now there are options here, we have to find out. So whether both are false or both are true, or one is true, statement 2 is false, or statement 1 is false and statement 2 is true. We have to see that. So what is the situation here? Look here, these are slit 1 and slit 2. This is the one, and see, this is central bright fringe CB, and this is suppose fast bright fringe, fringe. Okay, and this theta is actually angular fringe separation. Okay, and see this distance is generally denoted by x. We know x is how much? X is lambda capital D by small d. If you don't know, you have to just go for the derivation and see that. Okay, so this is the linear difference, okay, linear distance between central bright fringe and the fast fringe. Okay, or if you take, say, consecutive bright and dark fringes, generally this is actually called path difference from this point. Okay, central fringe, see, xn is equal to n into lambda d. See, this is lambda capital D by small d. This is the path difference. So this is for bright, and another bright, if I take xn plus 1, so this will be n plus 1 is equal to this. So this will give the fringe width if you take the difference. Okay, anyway, this is the thing you need to remember. So this is, so this is xn. Now let us see what is theta. See, we can write tan theta is equal to perpendicular by base. Perpendicular is x and base is d. If the angle is very, very small, then tan theta can be written as theta. This can be written as theta, and that is nearly equal to x by d. What is x? What is x? X is lambda capital D divided by small d into this. So this capital D, they will cancel each other, and theta will be obtained nearly as lambda by small d. And you can see in this expression there is no capital D, or there is no dependence of fringe like slit to screen distance. Okay, there is no role in this angular separation. In this angular separation, there is no role of this screen to slit distance. So that's why the first statement is false. Okay, first statement is false, and the statement second one, let us see whether it is true or false. We have to see that the theta is directly proportional to lambda. Theta is directly proportional to lambda. So if the lambda is larger, if the lambda is larger, if lambda is larger, then angular separation decreases. This is not true. This is also not true. So this is anyway not true because it does not depend on the slit to screen distance. And second one is actually angular separation is directly proportional to lambda. So it should increase rather decreasing. Okay, so we can say both the statements are actually false. So the first option will be the correct answer here. Now I think this is the last problem for today. The potential energy of a long spring when stretched by 2 centimeters is Q. See, if I have a spring with its original length x1, suppose, and when it is stretched to some length x2, then there will be change in the length delta x is equal to x2 minus x1. Okay, all right, or let us say that is x. Change in the length is x, and potential energy stored in the spring, this elastic potential energy that will be stored in the spring is, that is given by U is equal to half k is the spring constant into the x square, or the change in the length, square of change in the length. So here if it is stretched by, that means this is first of all x1, suppose it is x1 is 2 centimeter, then this has value U. Okay, so this is U when it is 2 centimeter. Okay, let me just write it. K, and 2 is 2 square, that means 4 and divided by 2, so it will be 2K. 2 into K is equal to U. Now the question is, if the spring is stretched by 8 centimeter, if the spring is stretched by 8 centimeter, that means now the change in the length, suppose it is capital X2, that is X2 minus X1 now. Okay, so if this is equal to 8 centimeter, then U will be half K. This spring constant remains the same, even though the spring is stretched. And this is 8, means this is 8 square, that means, you know, this is 32K. This is 32K, and that we can write as 2K into 16. 2K is how much? From this, 2K is U. Okay, 2K is U, so we can write 16 into U. Okay, so this is, let us say this is U prime. The potential energy is stored in the spring when the spring is stretched by 8 centimeter. The potential energy stored in it will be 16 into U. Okay, this was very simple. So I think I'll stop it here for today, and next day we'll take up some more problems. So thank you for your patience. Bye for today.